So allow me to continue with the load analysis or cooling load analysis for the blood bank refrigerator. As I said, it is also called as a product load analysis because the product which is to be refrigerated is blood, and the blood which is being refrigerated in our case, in the case study, for better understanding, I had taken it as 144 blood bags. So I am designing a refrigerator which is capable of storing 144 blood bags. Each bag can store 450 ml of blood. The blood's density is taken as 1.05 kgs per liter, approximately same as that of water, and that gives me a mass of 68 kgs. And then I said this mass into specific heat into delta T gives me the cooling load. This cooling load is the pull down load, and if I divide it by time, so the pull down load is 5141 kilojoules. And how do I calculate that? 68 into mass, which is mass, into specific heat, which is 3.6, into drop in temperature from 25 to 4, which is about 21 degrees centigrade. That gives me 5141 total amount of energy to be removed in kilojoules. And that, if I want to get in terms of watts, I need to convert that kilojoules to joules, that is multiply it by 1000, and then depending upon the pull down time, the denominator would be the time in seconds. So for example, if it's a 6 hours pull down time, I divide this 5141 into 1000 by 6 into 3600 seconds, and that gives me 238 watts as the cooling load. And if the pull down time is more, that is 8 hours, the load on the refrigerator is 178 watts. Now this was for the pull down, but there is also something called as the steady state load. Now you understand that blood, once it is brought to the blood bank refrigerator, when it is brought to the blood bank refrigerator, it is at ambient temperature, let us say 25 degrees centigrade, and it has to be brought down to a storage temperature, let us say 4 degrees centigrade. So that is a pull down. But once it is brought down to 4 degrees centigrade, we might require to store it for hours together, right? So that storing period, if you are continue to store it for hours together, that is called as a steady state load. So how do you calculate the steady state load, or what is called as a cabinet load or cabinet heat load? We need to factor in how is the heat transfer happening inside the cabinet from the surrounding into the cabinet from the surrounding. So one way is there is a transmission of the heat from the outside to the inside of the cabinet. The second is there is some load which is generated because of the equipments inside the refrigerator. And third is what is known as the infiltration load, that is because of some fresh air which is entering or escaping into the cabinet and increasing the load of this. So as we see, the cabinet heat load would comprise of three components. One is the transmission load, other is the infiltration load, and third is the internal equipment load. And as I mentioned, transmission load is the heat transfer through the walls of the cabinet, and it would account for the largest steady state load. The infiltration load would be from the openings. When you open the doors of the cabinet, the air would enter, that is the infiltration load. And the internal equipment load is because of the fans which are used inside for better circulation, or the lighting which is necessary to keep the things illuminated. Now, how do you calculate that? It is again calculated by a simple heat transfer principle. Let us take the calculation of transmission load. So for transmission load, what you do is that you calculate using the expression U, which is the overall heat transfer coefficient, into A, which is the surface area, into the temperature difference delta T. Right, now the temperature difference delta T, you can take it the temperature outside the cabinet as 30 degrees centigrade, and we had already mentioned that inside the cabinet we are maintaining the blood as 4 degrees centigrade. So the difference between the outside and inside is 30 minus 4, which is 26 degrees centigrade or 26 Kelvin. That delta T you have to multiply it by the cabinet area 2.8 meter square, and you have to multiply that with the overall heat transfer coefficient, which is U, which is 0.36 watt per meter square Kelvin if you are having a puff insulated door, right? You know that doors are to be insulated in order to prevent the heat transfer or minimize the heat transfer. So for a puff insulated cabinet door, we take the overall heat transfer coefficient capital U as about 0.36 watts per meter square Kelvin. And then how do you calculate the transmission load? We calculate the transmission load as U into A into delta T. So you can pause the video and then you can do this calculation 0.36 into 2.8 into 26, and you should get the transmission load as about 26 watts. The second part, as I said, is the load because of opening the doors, and we need to open the doors for taking out the blood, right, or for keeping the blood inside. So what happens is the cold air would escape out and the warm air would enter, and that would increase the load on the refrigeration system. Now for that, and we'll discuss it in some other lecture, what we do is that we need to do the calculation of enthalpy of the air which is inside the cabinet and the enthalpy of the air which is outside the cabinet by making use of what is known as the psychrometric chart. Okay, so psychrometric chart gives you the properties or enthalpy of the air, and that helps you calculate the infiltration load. But for a smaller systems like the one which we are dealing with, we can also make a reasonably good engineering assumption, and that could be around 35 watts as the infiltration load. Okay, so now my steady state load becomes 26 plus 35, which is the cabinet heat load. We need to add to that the equipment load. So for a blood bank refrigerator, I use say two fans, each fan of 5 wattage. So that gives me a load of 10 watts. So simply multiply the wattage of the internal equipment with the number of equipments, and that gives you the equipment load. So suppose there are two fans, each fan is of 5 watts, so that gives you a wattage of 10 watts. Similarly, if there is lighting of some ampere, some wattage, you have to add that. There are some controls that would also contribute to internal heat generation. So all in all, if you add them, then for this blood bank refrigerator of the size which we are considered, the approximate internal equipment load is 12 watts. So now you see, you need to have a good understanding of these numbers. You might say that why are you making an assumption? You need to first understand that the load which we are calculating, this internal load or infiltration load or transmission load, they are not going to matter a lot in the design of a blood bank refrigerator, because blood bank refrigerator has to be designed to take care of the pull down load, right? So without pull down, though the load appears to be less, steady state cabinet load appears to be less, which is 73 watts, but we need to consider the pull down load, which is substantial, 238 if it's a 6-hour pull down, or 178 if it's an 8-hour pull down, and add to it the cabinet heat load to arrive at the correct load estimation. I hope you understand this.